Okay, so I think let's get started. Hello everyone, welcome to this tutorial session. My name is Hao Liangli from the Department of Electrical Engineering of City University of Hong Kong. So the topic of this tutorial session is about the domain generalization, so which is to analyze the robustness and generalization capabilities of our AI model. So first of all, I would like to thank my colleagues who helped me to organize this tutorial session, including Dr. Jingnu Wang and Dr. Xin Xie from MSRA, as well as Professor Sino Pan from the Chinese U of Hong Kong. Yeah, so here is the outline of this tutorial. So as you can see, our tutorials consist of two different parts. So for the first part about the fundamental about this domain generalization, so which will be presented by me. And next, because you know that nowadays the AIGC, especially the ChatGPT, is very popular nowadays. So my colleagues, Jingnu Wang, will share with you his research experience about this robustness and generalization issue related to ChatGPT. Okay, so I'm working on the problem of computer vision, so which is actually quite similar to the data science and data mining problem. So for computer vision, our researchers has been analyzed this problem for many decades. So in the past, our researchers focus on the feature extraction, I mean the handcrafted feature extraction to tackle this computer vision problem. For example, one can utilize the age or line descriptor, right, to describe the image information. And then we can utilize this feature descriptor for different kinds of computer vision problem. Yeah. But nowadays, with the development of the deep neural networks, right, so we can see that we already achieve a lot of success by using the deep learning models for many different kinds of computer vision or even other kinds of computer vision plus data mining problem. And also, even our human beings, right? Many years ago, it has been reported that the deep neural networks can surpass our human beings' recognition successful rate. And also, in analog to the conventional computer vision problem, right? So where our human beings relies on feature extraction first, and then apply the extracted feature for many types of computer vision problem. So similarly, in the era of computer vision and deep learning, so one can also utilize the hidden layer of our deep neural networks. Maybe train on one specific task, and then apply this learned feature on the hidden layers for many other downstream computer vision problem. Okay, so since nowadays, deep learning is very hot for not only computer vision but also many other related problems. So can we say that we already solved the problem of computer vision? Well, the answer is actually no, right? So one of the reasons is that our model actually do not generalize well to the new domains, right? It's not like our human beings, okay? So, and then you may wonder, right, because our deep neural networks, right, are powered by this big data, right? So why not we just collect sufficient data, right, to train our neural networks, and then maybe we can expects a very good performance on a specific task. So actually, while big data is available, right, on some kinds of task related to computer vision, but in some other cases, right, big data are actually not always available. So the first reason is that because it's impossible, right, to consider the data in all scenarios, so which greatly hinder us to collect these sufficient and diverse data for a specific computer vision problem. And on the other hand, right, because we know that for some kinds of application like medical imaging, right, so data can be protected under the privacy regulation. So For example, the medical imaging problem, right? So although that it's possible for us to collect data, but in many cases, we're not able to share the data with others, right? Because this kind of data is protected under this privacy regulation. Okay, so now to tackle this limitation, right, where we don't have sufficient data, domain adaptation, right, is proposed to solve this problem, right? So the idea here is that based on the training stage, right, so we are not able to collect sufficient data, right? So then we're going to ask, right, so maybe during the inference stage, right, to a specific environment, right, or to a new environment, right? So whether it is possible, right, to train on the source domain data. The source domain data refers to the data that we are able, right, to collect during the training phase with the label information, right? So we want to adapt the source domain data to the target one. So the target one is the data that we are interested in for a specific application, right? So of course, right, because of this data, this kind of domain gap, right, between the data from different environment. So the source domain data, of course, the appearance, their well, in other words, their distribution of the source domain data can be quite different from the target one. So the idea of domain adaptation, right, is to see whether we can adapt, right, the source domain data, for example, here the ImageNet, yeah, to the target domain data. Although they are both images, right, but maybe their appearance can be very different. So the idea of domain, so the technologies of domain adaptation so far, right? There are many works appears in these years, and the technologies of domain adaptation can be many categorized into 3 different streams, right? So, for example, we can do the sample reweighting, right? So, which means that we only consider the data from the source domain, which are similar to the target domain, right? And then we only train the data which is similar to the target domain, or we can apply, right, to put more weight to the data similar to the target domain. So that's why we call this as sample reweighting. So another technology, right, we call this as the subspace learning. So the idea of subspace learning is that, okay, although based on the data domain, right, the source and target domain can be very different, but maybe we're interested in finding a subspace, right? So based on the subspace that the source domain data and target can be similar. So in this case, we can expect to train a more generalized model based on the target domain. And nowadays, because of the development of the deep learning technologies, right? So one technology is called the adversarial training, right? So we can also apply such idea of this adversarial learning, which was originally coming from the game-based method, right? So the reason why adversarial learning can be applied here is that, so in the original game paper, right? So the researchers show that by performing this adversarial training, this kind of pipeline is equivalent to minimize the JS divergence, right, between the source and target domain. So therefore, by performing the adversarial training, we can treat this as aligning the JS divergence between the source and target domain, right? So in this case, we can expect that based on the feature space, these 2 domains of data can be similar, right? So therefore, the robustness, the generalization of our models can be improved. But here the problem is that, as we can see, right, for this domain adaptation, is that we all assume that, right, no matter we do the sample reweighting or do the subspace learning, we assume that the target domain, although unlabeled, right, should be available, right, during the training phase. But actually in practice, especially for online, the real-time application, right? So this kind of target domain is actually not available during the training stage. Right, so we want to ask, are we able to collect this unlabeled testing data, right, during the training phase? And just as I mentioned, the answer is actually no, right? So one reason is because we want to apply this for the real-time deployment purpose, right? So for for this kind of case, we are not able to collect this sufficient number of unlabeled target domain data during the training stage. What we can only rely on is the source domain data, right? And of course, because of the data privacy regulation, right? So in some other cases, right, you are not allowed to use this target domain data during the training phase, either because they are protected under this privacy regulation or some other reasons which that we are not able to use during the training. So that's why, right? So we focus on the problem of domain generalization. So the idea of domain generalization, right? So because we don't have the target domain data, right? So but we assume that we can collect maybe some data, right, under some particular environment during the training stage. So we want to ask, right, so whether it is possible, right, to build a system for the previously unseen data set, right, given the one or multiple training data set. But of course, right, because the target domain is not available, right, so we always have the assumption that the target domain should be related to the source domain. Otherwise, we are not able to generalize, right? So here I show you one visualization example, right? So for example, the bike recognition, right? For bike recognition, because we have different kinds of brand of the type, and also we also have different kinds of background for the images, right? So the idea here is quite intuitive, that the background information we are not able to control, actually, right, during the training stage. So it's highly likely that the testing data can be very different from the training one, although they all belong to the bicycle. So now for domain generalization, we aim to tackle this problem, for that. So actually there are many methods, right, to deal with the domain generalization problem. So here I list few of them. So including like data augmentation and data generation, and also the distribution alignment, also similar to the idea of domain adaptation, right? And also we can apply the meta-learning, and also the contrastive learning and adversarial training can also be applied to this problem. So then I'm going to introduce some typical works of this kind of directions for domain generalization. Okay, so the first part is about the data augmentation, right? So the idea by applying the data augmentation for the problem of domain generalization is quite straightforward, right? So because the limitation of domain generalization is that we are not able to collect sufficient data, right, during the training phase. So maybe one intuitive idea is that, okay, so since we cannot have sufficient data, so why don't we do data augmentation, right? So for example, based on the image domain, we can manually apply the rotation of the image, and also to inject the noise or apply this color manipulation of the image, right? So this kind of methods, right? We call this as domain randomization, right? So can be applied here. So the idea is actually to randomly, right, draw some images, right, belong to different categories from the image net, and then we can apply this stylization and also the synthetic images based on this training data that we can have, for this problem. So here I show you one example, right? Apply this idea to tackle this problem where the data are not sufficient during the training phase, and we could find that the performance can be actually improved to some extent. So of course, right, so here is another kinds of method, right? So instead of doing that like data augmentation through some signal processing, image processing methods, we can also rely on the graphic software, right, to do this domain randomization. So which leads to this synthetic data, right, to the real-world data adaptation. And also because here the example that I want to give is based on this computer vision and image related problem, right? So for image problem, actually the context information among different objectives, among different objects, right, can be very important, right? Because in many cases, we cannot just randomly put the objects on different places, right, in the image. So therefore, the context-aware randomization can also be applied, right? By, for example, in this work, the author proposed like by considering this context information as well as the structure information, right? So where a structured domain randomization method is proposed based on this probability generative models, yeah, for the domain generalization problem. Okay, so here is about some way how we can apply this domain randomization to solve this problem of domain generalization. So of course, right? So just similar to many other works focusing on the robustness of our machine learning model, right? Especially the adversarial sample. So similar idea can also be applied, right? For example, the adversarial data augmentation. So of course, originally, right, this idea is actually applied to maybe to encounter these kind of adversarial attack, right, to help to improve the robustness of our deep neural networks. But of course, a similar idea, right, can also be applied to the problem of domain generalization by considering as the adversarial sample, right, also as a data augmentation method, right. So we can also apply this the original data together with this adversarial sample, right, to help to build a more robust AI models, right, which can be expected to be better generalized. Okay, so besides this adversarial data augmentation, we can also perform this data generation, right? So the data generation is similar to other machine learning methods. For example, we can utilize the generative model such as the VAE and also the GAN-based method, right, to generate this kind of novel data. And utilizing this kind of novel data during this training phase, which help us to improve the generalization capability of our model. And besides, right, one can also apply the techniques called mix-up, right, which also finds to be quite effective for this generalization capability. Okay, so here I want to introduce some other kinds of techniques which are also based on this data generation, right? So besides data generation, because one assumption for our domain generalization is that in some cases, right, we can have the data from multiple environments. We call this as the multiple domain. So therefore, another strategy, right, to conduct this data generation is perhaps we can utilize this image stylization, right, to consider the content and also as well as the styles, right, among multiple domains. So therefore, we can do like the combination, right, to generate novel data, right, during this training phase. And thus our model can, the generalization capability of our model can also be improved. Okay, so here is also for this, the mix-up, right? So the idea of mix-up is also, you can treat this as a data augmentation proposed method. And so here I also show you that, show several techniques, right? So how similar ideas, right, can be applied also to the problem of the domain generalization. So as you can see, right, so for this data augmentation based method, so the idea are to some extent, right, coming from other areas, yeah, but still effectiveness can be observed, right? So for this domain generalization to help our models to be better generalized to novel samples. Okay, so this is about the data augmentation part. So the second part will be the representation learning, right? So so the idea of representation learning, right, is whether we can learn the features, right, or we call this as environment features, right? So this kind of feature, we expect this to be shared, right, across the domains. And if this kind of feature can be better shared across the domains, and then we can also expect such features, right, to be generalized to these unseen but related target domains, right? So here, maybe I want to give you one examples about this animal recognition, right? So for example, if we do not apply this environment representation learning technologies, right? So maybe, for example, based on this cat and dog recognition, right? So given the cat image, right? So maybe we can overfit to the ear information, right? So although ear information can also benefit cat recognition, but this can be overfitting because some other kinds of animal like dogs also have this ear, right? And so that's why we want to apply this environment feature learning to only extract this kind of environment feature across the domains. For example, here that we expect the model, right, can be better generalized. So the first method for this representation learning is based on this kernel method, right? So this kind of kernel method is also similar to other kinds of classification problem like support vector machine on the by using the kernel method, right? So the idea here is that whether using this kernel method, right, we can learn this domain environment information. So for example, we can apply the idea like domain environment component analysis, and also similarly, we can apply the transfer component analysis. So this kind of idea, so the idea is very quite similar, right, to some extent, which is that we want to minimize the distribution across the domains, right? So because based on the idea of the machine learning problem, one reason that machine learning is very successful lie on the assumption that the training data and testing data should be similar, right? So therefore, by applying this environment component, domain environment component analysis, this kind of kernel method, we expect to minimize the distribution across the domains. But meanwhile, we also want to preserve, right, the specific information, right, intra-domain, based on the intra-domain, right? So therefore, we can do a trade-off, while we can preserve the domain-specific information, but meanwhile, we also minimize the domain distribution, right? So we can improve the generalization capabilities of our machine learning models, right? So here, as just mentioned, right? So the idea for this generalized feature learning, right? So we should minimize the distribution, right, across the domains. As such, we expect our model can be better generalized. So how to select, right? How to choose a proper distribution measurement, right? Is considered to be important. So actually, the researchers found out that some of the distributions, right, proved to be quite effective for different kinds of problems. For example, the maximum mean discrepancy, right? So which is a very popular distribution measurement, right, between two domains. So one can apply this by minimizing this maximum mean discrepancy across the domains. We can expect that the model can be better generalized. But of course, because the target domain is not seen, right? So we also have to introduce some regularization term on the feature space in case that our model may overfit to the source domain instead of the target one. So besides the maximum mean discrepancy, one can also utilize some other metrics like the KL divergence, which is also for this distribution alignment, as well as we can also consider like the second order moment. For example, here the correlation alignment, right? So we can apply this kind of distribution measurement by minimizing the distribution across the domain, we expect to learn the shareable information, and such information is supposed to be better generalized. Yeah. Okay, so as I just mentioned, right? So yeah, by applying this distribution alignment, right, across the domains, we expect to learn this shareable information. But of course, the target domain is not available, unlike the domain adaptation, right? So which means that it is possible that we may overfit to the source domain, right? So to avoid this problem, right? So we can always introduce some regularization. So for example, in this MMD AAE works, so besides, right, utilizing these MMD laws, right, to extract shareable information, one can also introduce two additional terms, like one is the autoencoder term, to ensure that the latent feature preserve sufficient information as much as possible, right? So besides, we in this work, this adversarial training idea is also proposed by matching the latent feature, the distribution of the latent feature space, to a predefined prior. So yeah, so here maybe we can choose the Gaussian prior, or we can also choose the Laplace prior, right? So the Laplace prior compared with the Gaussian prior, Laplace prior can also introduce this kind of sparsity based on the feature space, so which also benefit this feature learning, right? Has been proved in a lot of works on these feature learning areas. So besides this MMDAAE, so we can also utilize the GAN-based method, right? So the GAN-based method is that this kind of the domain flow, right, methods can be applied, right, through these adversarial laws. So because as introduced, right, this kind of adversarial laws can be treated as minimizing the JS divergence, right, between two distributions. So such JS divergence is also similar, yeah, to the minimizing the MMD, as I just introduced. Okay, so besides the besides minimizing the distribution gap, right, across the domains, so one can also think about, okay, instead of the distribution, why not we just focus on the sample, right? So therefore, the contrastive learning, right, across the sample can also be applied. So the idea here is that although the data are coming from different distribution, right, so they may look quite different based on their appearance, right? But they share the same label space, right? And also we are going to utilize this data for the same task. So therefore, on the latent feature space, right? So the data share the same category, right? Although the appearance is different, but based on the feature space, they should be similar, right? So that's why in the feature space, we can focus on minimizing the feature distance based on the samples from the same category. Otherwise, we can propose to maximize, right, the feature distance, right? So yeah, across the domains. So this kind of contrast learning also has been proved to be quite effective to improve the generalization capability of our model. And of course, right, one can also apply the idea, right, for both this sample-based alignment as well as the distribution-based alignments jointly, right? So in this way, right, yeah, these two works found out that better performance can be achieved. Okay, so yeah, besides this, besides directly applying this feature alignment, right? So one can also think about applying this feature disentanglement, right? So the idea of feature disentanglement, right, is to consider to disentangle the latent feature to the domain-specific information, right? So maybe this domain-specific information is more related to one specific style, right? And also another information we want to disentangle is the domain environment information, right? So therefore, we have this domain environment plus this domain-specific information. right? So where the domain environment information is, we expect this, right, to be generalized better. So for example, in these works, the authors, right, apply this environment feature learning together with this style transfer, to learn this shareable informations across the domains for the problem of domain generalization. And it has been shown that also some desired performance can be achieved. Okay, so nowadays we are all doing this deep learning, right? So deep learning is actually based on cascade manners. So which means that we have multiple layers, right? Available, for our deep neural networks. So just now we highlight, right? So this kind of feature learning can be important, but we miss this the importance of the this kind of shallow layer and also the deep layer, right, for the problem of domain generalization. So the idea here for this multi-layer feature learning is that based on the observation that the deep features, right, so eventually transit from the general to a specific along the networks. So for example, so here I want to give you the cat example for illustration purpose, right? So as you can see, based on the shallow layers, right? So when we extract a small related like the age, the contour information, right? But the deep layers, we can extract more semantic information, right? So this kind of semantic information can benefit, right? This kind of the learning problems, right? So yeah. So here the idea, right? So for the multiple feature learning, right, is that the shallow layers, right? So is actually to extract this shareable information, right? So maybe it's provide us a hint, right? So maybe these shallow layers may be more suitable, right, to perform this distribution alignment techniques, right? But the deep layer extract more category-specific information. So therefore, it's natural to ask whether some regularization can be imposed on these deep layers, right? So therefore, a multiple layer feature learning can be introduced, right? Also for the problem of this domain generalization. So similarly, as you can see, based on the shallow layer, right? So we can apply this the domain alignment loss, including like MMD or adversarial training, or even the cover loss, right? Can be applied for this domain alignment to extract shareable information. But at the deep layers, right? So what we expect is to extract more category related information, right? So this kind of category related information, so for example, can be extracted by considering this neural independence regulations. So which has been found that, by jointly applying this multiple feature learning, right, we expect that the better generalized information can be learned, which help to improve the generalization performance of our AI model. Okay, so lastly about this the domain environment learning, right? So just now what we introduced is to consider like distribution matching as well as this contrast loss, right? Based on a single sample, right? But the problem here is that, right? Okay. Directly performing this either distribution matching or this contrast learning, there's still a risk, right? Our model can be overfitted, right? So to further reduce the risk, right? So one can introduce this uncertainty learning, right? So this uncertainty learning also has been discussed a lot, right, in the community of machine learning. For example, we can apply this Bayesian neural networks, right? For this uncertainty modeling, and we can also apply this uncertainty modeling through this reparametrization tricks. So the idea for this uncertainty modeling is that each sample now is actually a distribution, right? So for example, through this Bayesian neural networks. So given the sample, we actually, we can also do the sampling, right? Based on the sample. So now a sample is now considered to be a distribution. So in other words, we can also treat this domain environmental learning with uncertainty as another types of data augmentation. Right, so which help us to reduce the risk of overfitting when performing this domain environmental learning. Okay, so that's I think that's all about this feature representation learning. So actually, there are still many other methods, right, for the domain generalizations. So for example, one can perform this meta learning, right? So the idea of meta learning is actually coming from this multiple task, right? So but at a high level, so there's still some similarities, right? So as such, our researchers found out that meta-learning can also be applied to the problem of domain generalization. So besides meta-learning, we can also utilize this ensemble learning, right? And so the third type is we can also learn generalized models, right? So maybe through the gradient operation, which I'm going to introduce later, right? And also one can consider this distribution robust optimization as well as this self-supervised learning. So next, I'm going to introduce them one by one. Yeah, so the idea of this meta learning, right, is proposed, right, for this learning to learn, the idea of learning to learn, yeah, or to meta learn the general knowledge. So the idea, right, for the meta learning, as mentioned, actually has been applied to this multiple task learning, right? So the idea for meta-learning is that instead of the original task, right? So we want to acquire the knowledge, right? So how to apply the knowledge from the old task, and which can be generalized to a new task, right? So here is the idea. So how this meta-learning and the multiple task learning can be linked. Okay, so here is the the formulation of this meta learning. So for the problem of domain generalization, so the idea here is that we want to apply such idea, right? So because meta learning is focused on this originally, right? Focus on this multiple task, but by treating different domain as different task, right? So we can apply similar ideas to the problem of domain generalization. Okay, yeah. Okay, so as mentioned, right, so how to apply this idea of meta-learning for domain generalization is, right, so we want to apply the knowledge learning from the old domains, right, from to the new domains in analog to the meta-learning for multiple task learning problem. So maybe the very first works, right, for by applying this meta learning for the problem of domain generalization is to the MLDG, which is short for the meta learning for DG, and also there has been many other methods being applied. For example, by applying this meta-reg, right? So meta learning for regularization. So here, as you can see, right? So here the all pipelines, right? So because for this original meta learning, right? So what we're going to do is that we already have the sufficient samples, right? So for some specific types of task, right? But what we are going to do for new task is that we also have few labels, right, for a new task. So therefore, we can have this like the support set as well as the query set, right, for this original meta learning. But for meta learning for domain generalization is that the domain, right, the data for target domain, right, is actually not available, right, during the training stage. So therefore, we want to simulate, right, this kind of domain gap. So in the first paper, right, which applied this meta-learning for domain generalization. So the idea is very simple, right? Suppose we have multiple domains available, right, during the training. So one idea is to do the splitting, right? Splitting, which is some part of the source domain data, right? We can treat this as the support set, and the other types of data, right? So we can treat this as a query set. So in this case, right? So we can apply the similar ideas, just like this ML, the meta learning, MAML, right, to the problem of domain generalization. Yeah. So here I summarize this pipeline for that. So besides these two works, right? So there are similar other works, right? For this meta learning. So of course, right? The meta learning is also not conflict with other problems of domain generalizations. So which means that one can also apply this meta learning with some other kinds of technologies, right? For machine learning problems, which can jointly improve the performance of the generalization capabilities of our AI model. So for example, in this meta VIB, right? So one can apply the idea of the meta learning together with the uncertainty modeling, right? Which I just introduced now. So to improve the generalization capabilities of this model. Okay, so besides, I also want to share with you some other typical works, right? Which also apply this meta learning for the problem of domain generalization. Okay, so besides meta learning, one can also apply this ensemble learning, right? So for our problem. So originally, right? So the ensemble learning, right, for machine learning is that we can have different kinds of models, right? Maybe different models can be trained by using different algorithms, or different models can be trained by using different data sets, right? So then we can performing the techniques like boosting, bagging, and also stacking, right, for machine learning problem. So here, one can also apply similar ideas for these ensemble learnings, right, to improve the generalizations of our model. So basically, in the community of domain generalization, right, so one can consider to do the ensemble learning based on two different levels. So the first level is based on the feature space, right? So the feature space can be learned from different domains, right? So for example, nowadays the deep neural networks are all equipped with this module called this batch normalization. So you can imagine that by applying different data set, right? So the parameters of this batch normalization can be very different. So which actually generate different kinds of model. So therefore, we can apply this ensemble learning, right? Based on the feature space. For example, based on the output of these batch normalization layers, right? To see whether some better performance can be achieved, right? So besides the feature level, one can also apply the one can also apply the this ensemble learning, right, based on this the classifier level, right? So the classifier level. So for example, in this works, right? So the figure on the left. So this also proposed to use the pre-trained model without this. They call that without the fine tuning. So the idea here is that one can utilize this kind of pre-trained model, for example, on the ImageNet, right? So for image classification problem. But of course, if we just want to utilize this pre-trained model, the label space, the category space of this the model pre-trained on ImageNet compared with the model for our own specific task can be very different. Right. So therefore, what they introduce is the adapters based on the pre-trained model, the output space of this pre-trained model, and then followed by this adapter, we can convert the label space from the pre-trained model to the label space of our interested of our targeted task, right? So after that, the Ensemble network can also be introduced to aggregate the output from different pre-trained model for the final prediction, right? So that's how Ensemble learning can be applied, right? So for this based on the classifier level. So besides this work I just mentioned, so here, right? So we can also apply this, right, by considering this data augmentation together with the classifier trained on the multiple domains, right? So, for example, in this work, the DAEL, right, they call this as the domain adaptive ensemble learning. So, the techniques, right, in this paper, right, so is that because in most of the cases we can have multiple domains, right? Suppose we can have k domains in total, so therefore we can train k different classifiers, right, for this specific problem. And then meanwhile, based on the targeted domains during the inference space, right? So we can apply different kinds of the augmentation types on the target domain. So we want to enforce that this augmented data through different the classifier trained on different domains to be similar, right? So that's why there is a consistency loss. So yeah, so that's how you can see that this ensemble learning, yeah, can be applied here. Okay, so finally, for ensemble learning, right? So we want to ask that whether it is sufficient for the problem of domain generalization, right, compared with other methods. So actually, the answer is no, right? Because this ensemble learning actually still the objective is to extract the domain-specific information, right? So still, the domain environment information is very important, right? To help to improve the generalization performance of our model, right? So as you can see here in these works, right? So both the ensemble learning as well as this environment feature learning, right, are proposed. Right. So based on this, the visualization of the features. So as you can see, right. So by considering both the ensemble learning together with this domain environment feature, right. So better feature space, right, can be learned by jointly considering these two. Okay. So now is so I finished the part of ensemble learning. So now I want to introduce the third part, so which is about this gradient operation. So this gradient operation for domain generalization, right, is quite interesting, right? So you may wonder why gradient can be applied, right? So so the idea here is that gradient actually determines the optimization directions, right, of our models, right? So for different kinds of domains, right, although the data are coming from a different environment, but since this kind of data are all based on the same problem, right? So intuitively, you can think of this as their optimization direction should be similar, right? So therefore, we can enforce the gradient similarities across the domains, right? So therefore, we can expect that the generalization capability can be improved. So these gradient similarities can be improved by many methods. For example, we can consider the inner product, right? By maximizing the inner product across between two domains. So we can force that the optimization direction of these two domains can be similar, right? So therefore, we can claim that generalized information can be better learned by doing this. So besides the inner product, right? So one can also apply this the L2 norm, right? So the L2 norm and the inner product at a high level, right? So you can think of this to be similar, right? So maybe claim by this, right? So based on this optimization direction, right, may not be fully supported by this mathematical theory, right? So, but another explanation, right, so why this kind of gradient operation can be applied for domain generalization is based on the recent advance of this neural tangent kernel. Right, so the neural tangent kernel theory tells us that, so by applying the Taylor expansion, right, of our deep neural network, so the gradient information, right, actually can be treated as the feature space of the deep neural networks, right? So by maximizing this inner product, or by minimizing this gradient L2 norm, so we can also treat this as minimizing the feature distributions, right, across the domains. But the feature distribution is based on the neural tangent kernel space, based on the gradient instead of the latent feature space. Yeah. So this is another explanation for this gradient operation. Okay, so similarly, right? So in these years, right? So there the self-supervised learning, right, turned out to be very popular. So the idea of self-supervised learning is that, right, so we also witness a lot of models like CLIP, right? They all based on the self-supervised learning. So therefore, how this idea, right, self-supervised learning can be applied for domain generalization is that maybe we want to introduce some auxiliary task, right, beside this classification task or some other kinds of task specific loss for this problem. So for example, the way like the contrastive loss, right, as I just introduced, can be also treated as a self-supervised learning. So in other words, besides the classification loss, right, so we can also consider the contrastive loss just as the data, the sample distance minimization, right, across the domains. We can apply this the min-max by considering both positive and negative samples. Meanwhile, we can also consider this the positive samples without the guidance of the label, right? So one idea is that based on the original data, one can also apply the data augmentation, right? So therefore, this kind of the contrastive loss, the data pair for contrastive loss, can be applied. So another method, this kind of jigsaw puzzle, right, can also be applied. So as you can see in this jigsaw puzzle, right, so another task besides the classification, image classification, right, so they also introduced this jigsaw classifier, right. So this jigsaw classifier can be treated as additional auxiliary task, right? So we found that, some better generalization can also be achieved. So of course, besides the techniques we mentioned, there are some other kinds of self-supervised learning methods can also be applied, right? For example, the rotation prediction, something, right? Although we don't have the label information, but we can generate a lot of auxiliary labels, but not for classification, but for this rotation prediction, image rotation prediction. Right, so this kind of method can also be applied. So we all call this as a self-supervised learning-based method. Okay, so so the fourth part is the we call this as the distribution robust optimization part. So the distribution robust optimization, right, for this domain generalization, right, is actually we want to utilize this worst case. The worst case data, right, for doing the training stage. So this kind of method is also similar to the adversarial augmentation, right? So we want to apply this adversarial augmented, right, data for our problem. So here we want to for this kind of distributionally robust optimization for domain generalization is that we want to learn a model, a worst case distribution scenario. So one example for this distribution robust optimization is that, right, so we can consider, right, so based on the idea of machine learning, right, so we expect that a feature space, right, for our machine learning, right, to be the manifold of the feature space, should be smooth, right, something like that. But actually, when coming to this problem of domain generalization, when learned the representation, the feature representation from multiple data, right, so the feature space actually turns out to be very, very strange in many cases. So one idea, right, to do this distribution robust optimization, right, is to consider all the data points, right? So for example, here in the first figure, right, so maybe we can have the data from 3 different domains. We call this as maybe 1, 2, 3, like that. So what we want to do, right, is to perform this convex hull, right? So as such, we expect that the data can fill the holes of the manifold, right? So by considering this convex hull, this combination, right? So we expect that the feature space can be more smooth. So in such case, that the generalization capability can be improved. But here the problem for this work is that only the convex hull is considered. But for our domain generalization, right? So you can imagine that this convex hull may not be optimal, right? Because the data for testing can always lie outside the convex hull, right? So for the first work, we only consider this linear combination based on the convex hull. But the data, right, outside the convex hull has been largely ignored, right? So that's why in this work, an extrapolation, right, based method is actually considered, right? So the formulation is actually like this. So mathematically, you can imagine that you can see that the equation, right, for the first part and the second part looks similar, right? But actually, it is not. For the first work, the combination is only based on the convex hull. There is a regularization of the weight, the combination of the weight, right? So which requires this convex hull regularization. But for the second one, actually, this combination weight, right, lambda e, right, actually can be a negative number. Right. So as you can see, once this lambda e is a negative number, so it is no longer this linear combination based on the convex hull, right? So that's why extrapolation can be done by doing so. So here is the distribution, the idea of the distribution robust optimization. Okay, so of course we have some other interesting learning methods for the domain generalization. So for example, right, based on the computer vision, right, so of course there are some prior knowledge to be involved, right? So when performing this machine learning for image classification, for example, based on image, we know that the shape information actually is very important, right? So why not we just extract, right, to do some pre-processing first, right? So we call this as a shapelet feature. But of course, for this kind of problem, the domain knowledge, or we call this as a problem knowledge, is very important, right? Because such method may not be applied to like NLP problem, to other data mining problem, right? Because for some other kind of data, we don't have this kind of shape information. So of course, right? So we can also apply some other methods, for example, to analyzing this the loss landscape for that. So the idea is based on the idea that this kind of technology is based on the idea that deep neural network is considered, right, to be very high nonlinear, right? So high nonlinear means that there are many minima, right, could be found based on our loss space, right? So but which minima should be better generalized for our problem is that the flat minimum, right? So there are a lot of research works they discuss about how this kind of the log landscape can influence the generalization capability of our model. So instead of like only applying this the loss functions such as the cross entropy to find the minimum, we can also add some regularization. right? So this regularization can be that, okay, we only seek the, we are only interested in finding the flat minimum instead of other kinds of minima. So in this case, right, so we expect that better generalization capability, right, can be improved by doing so. Yeah, okay, so yeah, I think that's all about these kinds of the problem of how this kind of learning technologies can be applied for domain generalization. So for the next session, I want to introduce some applications, right? So because we know that the problem of domain generalization is actually aims to tackle the problem that we do not have sufficient data, right, during the training. And this kind of scenario, right, the insufficient data can be applied to different kinds of application, right? So just now I focus a lot on the computer vision, right? But of course, some other kinds of application in the field, such as the natural language processing, and also like robotics, and also some others like this time series data processing, in this field. So here is the figure, right? So which just summarize some typical applications, how domain generalizations can be applied in different kinds of field, right? So so here the figure is coming from the survey paper of my colleagues, Dr. Jin Nongwen. So if you're interested, you may want to to take a look at the paper to see whether there are some application that meets your interest. Okay, so here I want to do a quick summarizations, right? Maybe about some specific problems, right, where we encounter the problem of domain generalization. And also maybe I want to introduce some benchmarks in our research community, right? Yeah, so here is for the computer vision, right? So for the first one is actually a very popular data set called, actually it is one of the pioneer data set, right, in this research community called this PACS. So namely, right, so as you can see, so the data from 4 different data sets. The photo are painting, cartoon, and sketch. They look quite different, right? But they all belong to the same category, right? But the limitation of this data set is that you can see that this is quite toy, may not. This data set can be used as a very good example, right? As a proof of concept, but still there is a gap, right, between the research works together with the real world applications. So besides that, we also have this action recognition, right? So compared with the image classification, the challenging for action recognition maybe can be the capturing angles of our action, right? So because the angles are coming from different cameras, so we can see that the appearance of the actions can looks quite different, right? So we have a lot of like deformation, a lot of hiding, this kind of problem. So that's we are going to tackle. And similarly, we also have this like similar to action recognition. We also have the similar problems for like person read ID, right? So for this person read ID, we also encounter similar problems like the capturing angle, but also besides the angle, we also have like the lighting condition, the environment, right? And also because of this, nowadays I think like the CCTV cameras are widely used this wireless based camera, right? So for wireless camera, we also need to consider like this kind of compression, right? This transmission noise, which we should consider related to different kinds of environment. So here, right, last but not the least, I want to introduce this segmentation, right, which is widely applied. So here is the based on the road sim, right, which is widely applied in the scenario of autonomous driving, right? So this is also very challenging, right, because we know that for different city, the layout can be very different, right, in many cases, and also the challenges such as the environment, like the lighting, also like the weather, right, can also be encountered for this kind of semantic segmentation problem. So how to tackle this problem? It's still many people are working in these areas even nowadays. Last but not the least, I want to introduce now maybe closely related, right, to the problem of domain generalization, which is the style transfer. All right. So as you can see, based on the techniques I have introduced, so in the field of domain generalization, the researcher also apply, right, many ideas, right, coming from the style transfer, right, for this data augmentation problems. Yeah, like that. Okay, so here is the computer vision. So here I want to introduce some others, right? So for example, the natural language processing. So for example, the sentiment classification, right? So here is the data set of Amazon data set, right? For different kinds of products, right? So maybe based on the review content, right? So maybe the style information can be very different. So each kind of style, right? We can treat it as a domain. Right, so you can imagine that, for example, training on this DVD dataset, the book dataset, the kitchen appliance, although they are all for semantic classification, right? But when applied to another kinds of good, right? So yeah, maybe the semantic information can be quite diverse, right? And also here is another example for semantic parsing. Right. So, but of course, these two problems are very old NLP problems. Right. Nowadays we have this ChatGPT, but even for ChatGPT, we still encounter the problem of this generalization issue. Yeah, which will be later covered by my colleagues Jin Nongwan. Yeah, so the third one is the reinforcement learning, right? So reinforcement learning probably one very exciting application is for this robot control, right? So for robot control, we always want to use the semantic data set, right, for the training, and then we want to apply the learning algorithms into the real world. So which leads to the domain gap between this synthetics data, right, together with the real data, right? So how to apply this the idea of domain generalization to solve this kind of problem, right, is also very popular nowadays. Okay, so also, yeah, this medical application. So medical application, right, can come from such challenging can come from this the data privacy, right? So although now we have a lot of hospitals, yeah, also we can collect a lot of data, but this data actually cannot be shared, right, in many cases. So that's why, right, federated learning, right, has been proposed, right, to tackle this problem. Yeah, but still, there are some other issues, right, which greatly hinder the success of this AI for medical imaging. One example is that when we do like the CT or MRI, right, so we know that the different populations, right, and also the different vendor machines. So this kind of factor actually we cannot control. And also this kind of factor can quickly hinder the generalization capability, yeah, for that. So for example, we have sufficient data maybe collected in Singapore and also Hong Kong, but now we want to apply our trained model to another area, right? Like one rural areas like that. So in this case, because of this the diversity of our population, right? So this kind of factors can also greatly hinder the generalization issues for that. Okay, so yeah, as you can see, right, so the problem of domain generalization is actually raise a lot of attention as well as discussion in our research community. There are a lot of the people from both academic and also industry are working in this area. So of course, one of the important thing is we want to construct the domain generalization benchmark, right? So when we coming up with an algorithm, right, how can we tell, right, whether our algorithm performs good or not? Of course, one can apply the algorithms on our own collected database, right? But still, it's not clear whether our proposed algorithm really works well compared with other methods, right? So that's why the domain generalization benchmark is actually very important. Yeah, so there are many things needs to taken into consideration, right? Like the data set and also the code, right? Should also be fair, right, for different kinds of problem. And also evaluation, yeah, is also very important. All right, so maybe I want to introduce some common benchmarks, right? So yeah, here the PSA, as I already introduced, right, is for the computer vision, although very toy, but still being widely used nowadays, and is considered to be one of the benchmark in the popular domain bed, right, which I'm going to introduce later. And also VOCS and Office Home is also for computer vision. But as I just mentioned, right, so the problem for domain generalization is actually beyond computer vision, right? So in many kinds of application, we all encounter the issue of this generalization. So that's why recently a popular data set called WILD, right, has been proposed here, right? So the WILD is that besides the computer vision problem, it also consider, right, some really challenging data set, maybe related to computer vision. For example, we have this medical imaging, and we also have this remote sensing, right, from the satellite. But besides that, it also contains some other kinds of applications, including like the drug discovery and so on. Yeah. So here is the one I want to introduce. So which is the domain bed, right? Domain bed perhaps is one of the most widely used data set in this research community. It consists of many data set, right, coming from both the computer vision, very toy one, yeah, but still widely used, and also consider some other challenging, right, data set. Yeah, so here is the figure of the data set we use, as well as the algorithms. So actually one interesting thing, right, is that, so based on this domain bed, right, so as you can see from the results, so actually perhaps one of the best algorithm is still the empirical risk minimization, right? So compare with other methods designed for domain generalization. So which indicate that this area, there are still many works needs to be done. Yeah, okay, so besides that, so here I also want to introduce this kind of algorithms, which is implemented by my colleagues, right? So which also contain some popular algorithms for domain generalization. So if you're interested in using this for your own problem, right? So please feel free, to try to your own problem. Okay, so how do we do this evaluation, right? So for that, so here I want to introduce like this model selection, right, for this domain bed. So actually, it has been 3 different kinds of strategies, right, has been considered, right? So for example, we can use the test domain for validation, and we can also apply like leave one domain out, right? So which is actually one of the standards, right, techniques when choosing the models, right, in the community of machine learning. So the last one is actually we consider this training domain and also the validation set, like that. So yeah, here is the visualization examples, right? So I show here. So how these 3 different technologies different. Yeah, and also, right, so it's quite common, right, to ask, right, so whether it is reasonable to using this training domain validation for this model selection, right? Just as our common machine learning tasks, right? So based on the training data, right, we can reorganize the data set into training and testing, right? So maybe you will want to ask whether such strategy can be applied here for the problem of domain generalization. The answer is actually no, right? Because the validation distribution, right, so is different from the target distribution, right? So in this case, right, the performance on validation dataset cannot reflect the real performance, right, of our generalization capability. Okay, so next, I want to show maybe some discussions about the performance of the domain generalization, right? So yeah, so of course, now we always want to ask, right? So whether it is possible, right, to come up with a universal algorithm, right? So which can be applied to all different tasks. Yeah, but still currently, right, in the community of domain generalization, still we found this to be quite difficult to do that. So therefore, nowadays we focus on the evaluation, right, based on the specific task. Right. So, for example, if we are doing like human activity recognition, so maybe we want to consider, right, maybe some prior knowledge for this human activity recognition and design an algorithm, and then for comparison, right, and then for the cross dataset object recognition, right? So then we want to consider, right? For example, maybe some prior knowledge for our image, like the shapelet feature, right? I just introduced just now, right? To consider them for evaluation. Okay, so I think for the last part of our first session, right? So maybe I want to briefly introduce about some theoretical work, right? So so far, maybe I think you found out that, right? The things I have introduced are all algorithm level, right? So there's lack of theoretical discussion, right? So, and also it's quite interesting to ask, right? Maybe we can find out theoretical work, which really can tell us, right? So whether our algorithm can be better generalized or not. So besides that, maybe I want to talk about this domain adaptation, right? So, which is very similar to domain generalization, but instead domain adaptation, we assume that the target domain is actually available, right? So for domain adaptation, actually we have a very elegant theory for that, right? So where our target risk is actually bounded by three different terms. The source risk, right? So the source risk means that the errors on the source domain, as well as the source target distribution divergence, and plus a constant, right? So as you can see, right? So for domain adaptation, what our researchers do is to minimize the source risks, right? And then meanwhile, we minimize the source target distribution divergence. So that's how, right? Many domain adaptation follow this pipeline, which is reasonable, right? Because this kind of pipeline is actually guided by the theoretical study for that, right? Okay, so here for this source target distribution divergence, right? So one can utilize, right? In practice, one can utilize a lot of distribution matching-based techniques, right? So which I have introduced, such as the MMD loss, such as the chaos divergence, and also like the adversarial learning, right? So which is equivalent to this JS divergence minimization. So for our domain adaptation, yeah, everything is very good, right? So yeah, but now, yeah, for the problem of domain generalization, we have a lot of problem, right? So the problem is that, okay, we don't have target domain, right? So how can we measure these generalization errors, right, for our domain generalization? So of course, one intuitive idea, right, is that, okay, so since we don't have this kind of target domain, so why not we just generate one? Right. So after generate this target domain, so then we can apply this kind of theoretical analysis, right, in a similar way compared with domain adaptation. Right. So, okay. So one direction. Okay. So yeah, maybe we can do the approximate the target domain, right, using the convex of the source distribution, right. So which leads to the error bound, right? So which is similar, right? Quite similar to this domain adaptation, right? So, but of course, the limitation is also quite obvious, right? Because the target domain can very likely to be outside the convex hull, right? So, although this theory, seems okay, right? But still, there are many limitations for this one. Okay, so maybe for another one, right? Environment risk minimization, right? So which actually address a lot of attention nowadays in the community of domain generalization, but also robustness learning, right? So the idea for IRM is that, okay, we do not consider matching the distribution like domain adaptation, right? So, but what we want to do is to enforce an optimal classifier, right, on top of representation space to be the same across the domain. So in other words, right, so we have two variables, right, which needs to minimize. So one is the feature learning, right, and also one is the classifier. So what we expect is that to learn an environment feature and where we can impose a unified classifier, right, which can be generalized to all the domains like that, right? So directly minimizing this term, right, of course, can be cumbersome. So that's why in this paper, the author proposed to relax the objective function by only considering, right, to optimize the feature learning, but by normalizing the classifier, right, to a unit vector as f equals to 1. So this is called the environment risk minimization. So of course, right, so although it did not impose this empirical risk, right, like that, but still there are still some limitations for that, right? Because the effectiveness of this environment risk minimization still rely on the source domain, right? How representative is our source domain data, and how large is our source domain data, right? Otherwise, if our source domain data is not that representative, there is still a risk, right? That this learned classifier, right? Although, right, can be optimal, right, for all the source domain, but because target domain is still different from the source domain, right? So the learning classifier may not be optimal for the source one. So that's why I put here, right? So so the theory of this domain generalization is still in infant, right? And still there are many works needs to be done to analyze the theoretical part. Yeah, okay, so I think that's all about this first part. So for the second part, I want to introduce some new settings about this domain generalization, and besides that, I also want to introduce, right? So how so far, right? So we talk about how machine learning can contribute to this domain generalization problem, right? But still, right? One interesting thing is that the domain generalization nowadays, because AI is now very hot, right? So still some other related areas in the computer science, like the software engineer. Yeah, so they also want to apply this AI to their own problem. So how we can apply by using different kinds of method, maybe coming from the system, right? How these kinds of ideas, right, can benefit the problem of domain generalization. And lastly, for my part, I want to link how this DG, right, domain generalization, can be linked to the model explanations. And then I want to show some limitations of our explanation methods. And then we can see that how by improving, right, these explanation methods can shed light on the generalization performance. Okay, so now I think it's coffee break. Thank you very much. See you later. Okay, let's continue. Thank you very much for coming again. So in this session, so I want to introduce some new settings about domain generalization, as well as to discuss how some other works coming from like computer system, and also the explanation which can shed light on this generalization issue. And then finally, my colleagues, Dr. Jinong Wang from Microsoft Research Asia, will share with you some findings about the generalization issues by applying the ChatGPT. Okay, so Just now, what we introduced so far is about the conventional settings of domain generalization. So which we assume that we have like one single or we have multiple domains available right during the training stage. How we can do data augmentation and how we can learn shareable informations between the data from multiple domains to learn shareable information to learn an environment. Feature representation, which we expect to be better generalized to the unseen but related domain. Yeah, so here is some new settings, right? Besides the conventional setting. So among the settings, basically I want to introduce two kinds of setting. So the first one is the involving domain generalization. So which is that we assume that there is a involving pattern, a trend of the observed domains, right? So how we can generalize better based on this setting. And the second one is that I want to talk about this test time, right? Domain adaptation as well as generalization, which also adjusts a lot of attentions, right, in both academic and also industry. Okay, so now let's first comes to the first part, involving domain generalization. So in practice, actually, we all have many scenarios, right? So which the involving environment can be included, right? Based on the application. So, for example, based on the automated driving system, right? So how we expect that our AI models, right, can be better generalized based on these involving environment patterns, right? Based on different timestamps. For example, we observe some data from the morning and also afternoon, and whether it is possible to generalize our model to the night, right? And besides that, we also have the disease diagnosis, right? So, for example, we have the data, right, coming from a specific person, right? Maybe in the age, right, ranging from maybe 0 to 50. So we want to ask whether we can predict, right, some the disease at the age of 60 or 70, like that. Okay, so that is basically the setting for this involving domain generalization, right? So mathematically, which is that we're having this data, right, based on the timestamps, right, from 1 to t. For example, we want to predict the data coming from the timestamps t+1, like that. Okay. So the first, so this work I want to introduce is to model this the latent structure weir, right? So the sequence autoencoder, right? So based on this probability model to tackle this problem. So the idea here is that two different kinds of distribution shift are considered. So one is based on the data, right? So we call this as a covariate shift. And another is based on the label distribution, right? So because in practice, it's highly likely that our label space can also be changed. We call this as concept shift. Okay, so how to model this, right? So one intuitive thing is because we are based on this involving domain, right? So involving domain refers to the case that there may exist a pattern, right? An involving pattern. So maybe we can think about to having a mathematical model, right? To model this kind of pattern, right? So for example, we can model the pattern from 1 to t, right? So therefore we can naturally, right, extend our model to the time at t+1, like that. So what this work doing here is to apply this Markov chain, right? Based on that. So to model this latent code. And after having this probability modeling, so a probability generated model, right, based on both the data, based on the label, as well as the latent variables, right, related to the concept, related to this the data, right, information, right? So for example, can be related to the domain specific category, right? Can be related to the domain environment category, model information, right? Can be modeled here, right? And then because now we have this probability generated model, right? So to solve this probability generated model, we have a very elegant tool, by applying this variational inference, right? So we can approximate the prior. So this kind of thing can be done by optimizing the ELBO, right? So we call this to optimize this evidence lower bound ELBO like that. So here is the objective function. So what we're going to do is to optimize this part to model this dynamics. Okay, so here is a framework, right? So because we have this kind of dynamics on the latent space, so therefore, this kind of model, right? So the dynamics actually can be modeled by some RNN model, right? For example, the LSTM, like that, and also here by using a similar way as like a disentanglement, right? So we can capture this environment as well as the domain-specific information, right? To do like that. And here we also model this in an auto encoder way to learn this pattern. And then during the training, we have the data as well as the label information, right? Based on the domains from the time like 1 to t. And then during the inference, for example, given the data from 1 to t, right? So then in this case, we only need to extract this domain environment information based on the data space itself as well as the label information. We can do the inference prediction. Okay, so here is visualization result, right? So as you can see, right? So based on this involving pattern, right? So this toy data set, right? And we have this kind of like the ground truth, right? Something is more like a half circle, something like that, right? So therefore, as you can see by applying this traditional ERM, so we are not able to model this, right? The dynamic change of this concept shift, right? So the ERM fail here, yeah, but by applying this this LSSAE model, right? So we can better capture this involving information, right? Based on both the data as well as the concept level. Okay, so besides this, the classification results, right? So we can also apply the similar idea to the generalization. Right, so we can generalizing the future data like that, and meanwhile we can also control like the what kinds of variance we expect to have. So for example, we have this random data sequence, and we can fix, right? So this this concept, or we call this as a category related information, right? So by fixing this information, we can see that we can generate this rotating, but all belongs to the single digit, right? But then by fixing like the style information, by varying this category information, we can generating like the rotation degree are fixed, but the category are variant, right? So we can also do disentanglement like that. Okay, so here is the first part I want to introduce. So the second part is that I want to introduce about some test time optimization, right? So test time optimization refers to the case. Sorry, I have a typo, right? Should be domain adaptation, like that. Okay, so the test time optimization refer to the case that, okay, so after we have a pre-trained label, pre-trained model. Yeah, sorry about that. Yeah, so whether based on the target domain data, right? So the target domain data, of course, is unlabeled, right? So whether we can utilize this unlabeled data and then apply some self-supervised learning method to fine-tune the model, right? As such, we can adapt our model, our pre-trained model to the target one, right? And the difference between the test time optimization together with the domain adaptation is that for domain adaptation, we assume that the testing data, the training data are actually available. The source domain data are available, right? But for test time, right, optimization, the source domain is actually not available, right? In our case. Okay, so actually in this research community, right, so we have a lot of works, right? For example, based on the images, right? Based on the source domain data, for example, the data are very clean. But for test data, right, so because of these different kinds of environment variation, right? So highly likely that our target domain data are cropped with noise information, right? So there already exists a lot of works, right, to talk about that, to talk about this test time optimization. So, but the problem here is that video kinds of things is largely ignored, right? Because for video has its own intrinsic properties, like this video compression, the video coding error, right? So, so in practice, when applying our model in practice, the video data, right, is also very important, right? So to tackle this problem, the idea is actually similar, right, to the images when doing this test time adaptation, right? So first of all, what we need to consider, right, is to apply this temporal coherence. So you can imagine that for video classification, right? So for video classification, although for different frames, maybe the appearance can be quite different, right? But all the frames are actually contribute to the same task, right? So therefore, in the latent space, right? So in the latent space, we think that there exists a temporal coherence regularization. So in other words, the feature space are supposed to be the same, right? So we consider this as a self-supervised learning loss, right? Which is similar to the self-supervised learning I have just introduced at the first half session, right? So by considering this as a self-supervised learning loss, right? So we can expect, right, to fine-tune the model to better adapt the pre-trained model on the source domain to the target data. So here the target data may can be a single data, right? Can be a single data for inference, and also this kind of tuning method are supposed, right, to not be that time consuming, right? Because in many cases, for example, our domain generalization application, we actually expect the real-time application, right? So here the fine-tune should be as fast as possible. Yeah, so here are some results, right? By considering these video kinds of things, right? So how we can better outperform, right, these image-based test time methods by exploring these video-related properties. Okay, so this is another settings, right? So to see some related to domain generalization and also raise a lot of attention recently, which is about the test time domain adaptation and test time domain generalization. Okay, so after the new setting, so maybe I want to introduce some other kinds of techniques, right? So which all aims to address a problem of domain generalization, but not from machine learning. But still, there exists some relationship, right, between this kind of method with machine learning. But the starting point are actually from another field. So the success of the deep learning, right? So it has we observe that there we can apply deep learning in a lot of fields, right? So not only the problem, the AI-related problems like related to computer vision, related to NLP, and also robotics, but even some other fields, right? So in our computer science community, for example, the software engineering, right? We can also apply this deep learning, right, to their problem, right? So, which means that the researchers, right, from software engineering, they are also quite interested, right, the robustness and the generalization issue of our deep neural networks. So, but unlike our AI researchers, right? So we mainly treat the deep learning as a machine learning, right? So we apply these machine learning algorithms and then to analyze, right, the deep learning based problem, right? So how they treat the deep neural networks, right, can be a little bit different, but still, right, still there are many things that can be shared, right? So so here is one examples, right? So, which is to see how the software engineers, right, so they compare with the traditional software development to the machine learning system development, right? Because at a high level, right, both the machine learning system can also be treated as a software, right? This kind of problem. So, So for traditional software, what they analyze, right? So what they do is that they are going to analyze the decision logic, right? So similar to our machine learning problem, so we have input and we have output and we have a function, right? So this function is actually a decision logic, right? So here, as you can see for this machine learning, so we can treat the developers as the training data, feature selection, and algorithm tuning. Like that, right? So which means that we can link the relationship between the deep learning together with the software engineering. Okay, so when coming to this, when we want to compare, right, with this machine learning system together with the software systems, right? So perhaps one important concept, right, to analyze the robustness of our software, right, is we treat this as the coverage analysis, right? So for example, right, yeah, so what we do, right, when considering this software quality assurance is that like the code or logic, right, based on our software, but they have not been covered during the testing, so we can find the bugs, right? So here, right, in the software, we can treat the bug as the out of distribution sample, right? So similar to our machine learning problems, right? So therefore, in the software quality assurance, we say that the full coverage testing is needed, right? So here I want to show some examples for the software quality assurance. So for example, we can analyze the code coverage, the statement coverage, and function coverage, right? And we can also analyze the control flow like that, right? So yeah, so here is how software people, right, to do their own problem. So as I have mentioned, right, the software people now, they also want to explore, right, the machine learning, specifically the deep neural network, right? So so starting from the point of software engineering, right? So they also try to apply a similar concept for the software engineering, right? So they want to treat the deep neural networks, right, as a software system, right? So as I just mentioned, right, so for software, right, so we have a lot of way to analyze the robustness, but unfortunately, currently, right, for our deep neural networks, right, so it still seems that accuracy, right, is still widely being adopted, right, to analyze the robustness, the reliability of the machine learning, the deep learning system. But the accuracy is actually, right, is not sufficient to tell whether our AI model is robust or not. So that's why you can see I show some examples, right? So how this software people apply the concept we call the neuron coverage analysis for the deep neural network testing. So from the very beginning, the system conference appeared in the SOSP 17, and also we see a lot of works, right, by applying the neural coverage for different kinds of analysis. Okay. So here I want to. So here is for testing, right? So so far I introduced this deep neural network testing, which is that we already trained the neural network, right? So instead of only measure the reliability of the deep neural networks based on accuracy, can we have some other measurement, right? So they say that neuron coverage maybe can be applied, right, as a hint for the reliability of our deep neural network quality. But we want to ask, right, so whether the concept we call the neuron coverage, right, can benefit the domain generalization. So domain generalization is actually doing the training, right? So we try to improve the reliability, the generalization capability of a deep neural network by applying some machine learning algorithms, right? So here, instead of simply using the neuron coverage, right, for the DNN, deep neural network testing. So we are also interested in whether we can apply such concept to training, right? So which benefits the domain generalization problem. So therefore, I want to do a summary again, right? So far, I have introduced for domain generalization. So our researchers rely on these machine learning algorithms like distribution alignment, like meta learning, like contrastive learning, and also adversarial training. So they are all actually have coming from machine learning, right, theories, right? So, but instead, I want to share with you here maybe another perspectives, right? So how we can improve the generalization capability of our neural network, right? So which is that we want to treat the deep neural network as a software system, like that. Okay, so so what we're going to do here, right? So we want to propose a neural coverage guided training, right? So instead of testing, we want to propose this to training. So one interesting thing for this neural coverage is that we want to guarantee, right, during the testing, we want to make sure to examine whether a neuron has been activated or not, right? So because for the code coverage analysis, right, if the branch of the code or if a block of a code has not been activated, right, during the testing stage, and then when you deploy your software system in practice, right, and input, right, maybe this input can trigger the blocks which has not been activated before, so a bug can happen, right? So like that. Therefore, for our deep neural network, so we can imagine that if a neuron has never been activated during the training stage, and then during the testing stage, right, a sample from the target domain activated that neuron which has never been activated during the training stage. Therefore, the error can also happen, right? So therefore, how we can link this software system together with this domain generalization problem, is quite obvious. So therefore, so we can see that a neuron, right, is inactive during the whole training process, but during the evaluation, right, this neuron is getting activated, so we have error like that. So now we want to analyze this domain generalization from the perspective of the software system engineering. Okay, so how do we tackle this problem, right? So the idea is quite straightforward. So we want to make sure, right, the neuron should be activated during the training stage, right? So then during the testing, we expect that the error, right, which caused by the inactive neuron can be reduced, right? So that's why, okay, we want to introduce this pipeline. We call this as a neuron coverage loss, right? So what we do is that, okay, during the training stage, we want to maximize, right? So we want to maximize the neuron coverage, like that. So here, as you can see, we treat this neuron coverage as a regularization term. During the training together with our, the task-specific loss. For example, the cross-entropy loss, right? Like that. Okay, so in this case, we expect that we can, somehow reduce, right, the errors, right, caused by these inactive neurons for this generalization issue. But is it sufficient only considering the neuron coverage? Actually, it is not, right? So because this neuron activation only consider the binary information, whether the neuron activated or not, right? But in our code, right, so you can imagine we also have the path, right, the decision logic flow for our code, right? So which means that the interaction of different code. So when coming to our deep neural network, which is the interaction of our layer, right, which has been missing. So therefore, we want to apply, right? So the idea of the control flow in the software, the branch conditions, right, to the control flow in the deep neural network, which we define as the neural gradient, right? So you can see what we do here is try to minimize, right? So we have the original sample, we also have the augmented sample, right? So what we do is to minimize the gradient distance. So as I have introduced, right? So this is also widely applied, right? So in the community of machine learning by treating the gradient as the feature space in the neuron tangent kernel, right? So we can perform as a contrastive learning doing that. But here our starting point is actually coming from the gradient flow, but somehow, right, our loss function, right, is somehow the same as the contrastive learning based on the gradient, right? So what we do is by treating this as a regularization term during this neuron coverage analysis, right? So here I show you some results of the by applying this neuron coverage, which shows to be proved to be quite effective, right? On some benchmark data set. So of course, right, as you can see, this neuron coverage actually is not contradict with machine learning, right, models. So which means that we have the potential, right, by applying this this neural coverage together with other kinds of machine learning techniques to jointly improve the performance, right? The generalization performance of our machine learning models, right? Okay. So one last thing I want to discuss here, which I found this to be quite interesting, is that the idea here, right, for this neuron coverage is that, okay, during training we have some neuron that has not been activated, right, by any of the samples, but during the testing we have a sample, right, which activate this inactivated neuron, which leads to the error term, right? So here we want to do a visualization term here, right? Is that whether our motivation really makes sense or not, right? So here, as you can see, the deep all here means that we only train, right? So for classification, we only train based on this cross entropy loss, right? So this NCDG refers to the case we apply this neuron coverage regularization. So as you can see, right, so we want to examine the neuron, right, so which has not been activated during the deep all, but when coming to a testing sample, right, so this testing sample, actually you can see that we activated something which has no semantic information at all, right, so which leads to this error prediction. But by applying this neuron coverage analysis, we can see that we can capture like more semantic information. For example, here, this person classification, right? So we know that the eye maybe can play an important role, right? Based on this semantic information. So we can see we can extract this category specific information which can benefit the final prediction output, right? So that's why we see here is a linkage, right, between the software coverage together with this AI explainability. Right, so here this visualization tool is done by using this network dissection. Okay, so here actually we see that there is a potential, right, to see how this domain generalization together with the explanation, right, the AI model explanation, right, the relationship. So actually there exists many works, right, so they try to understand how this explanation capability can benefit this domain generalization problem. So maybe here I want to show one example, right, so based on this PACS dataset, right, so based on this explanation actually, right, so here is the photo I copy paste from one paper using the explainability for domain generalization. So as you can see, right, so based on explanation here, we activated some meaningful information, right? So which is actually can benefit the final prediction. Although this the animal, right? So here the giraffe, their style can be very different, but we can see that similar information, right, based on the head information, can be extracted here, right? So we see that there actually the causality, right, can be shared across the domains. But we want to ask a question: is that whether we can believe, right, such visualization? So in other words, we want to ask whether we can believe such explanation method, right, by doing so, right? So here is the final part is that I want to discuss with the explanation through attention, right? So which is quite popular nowadays for the explanation. So yeah, so here I want to show is that the positive attention, right? So many works they highlight that this kind of positive attention rates can indicate the contribution effect, right? So for example, we want to take the VQA, right? So problem as an example, right? So here by for the first part, right? So what are the colorful pieces on the donut, right? So based on the explanation, right? So we can get the right answer. But after we do a masking, right? So then we want to ask again, what is the girl eating? But then after we apply the masking, we can get the wrong output, right? So therefore, which means that the current explanation methods may not provide us with sufficient information, right? So the explanation method can be harmful. like that. Okay, so the problem here is that, right? So the current method, so what they are focusing on is only the importance correlation, right? By only analyzing the magnitude, right, to the explanation. So they claim that the magnitude can denote this feature importance, but actually one thing has been largely ignored is the polarity consistency. So which is the sign, right? So the sign of the feature, right, can denote the polarity of this feature impact. Okay, so yeah, here is some discussion of these previous works. So for this importance correlation, so we want to ask and we want to examine, right, the current limitation of the for this explanation method. So what we're going to do is to propose a faithfulness violation test, right? That's what we call. So the idea is to measure the ratio of test samples violating the polarity consistency. The polarity, if you still recall that, denote the sign, right, of the features. So what we do here is quite simple, right? So given the test sample X and then explanation method W, right? So the W can be the weight importance based method, right? Like that. So what we do is to find the most influential features through this explanation method, and then what we do is to do the perturbation, right, by removing that feature. So this is a very common statistical test like that, right? So here the delta C refers to how importance, right? So how this removing the perturbation can influence our final importance. So what we're going to do is to check the explanation, right? So you can imagine if this is a positive, which means that this actually can lead to the negative, right, influence to our final prediction. Like that. So what do we want to do is to check if the explanation weight align with the feature impact, like that. So here is a violation task can be the violation matrix can be defined. Okay, so to understand the whether this the violation, right? So we want to design three kinds of experiments, right? So the first one is why do we need the faithfulness violation test, and also how existing method performed on the faithfulness test, and then what factors dominate these faithfulness violation issues, right? So here the first question, yeah, is that we want to analyze this on a VQA task, right? Is to understand, right? So how this different explanation method, right, compare with the violation. So actually, you can see that under different kinds of violation, right? So we see that the different explanation method, their performance are quite similar, right? So which means that existing method may not show this faithfulness, right? So we point out the limitation of existing method, right? So which means that, okay, so the existing matrix are incapable of examining this polarity consistency, which indicate a new matrix has to be developed here. Yeah, and also here we want to show that the so what is the relationship, right, of this existing testing method? We analyze quite a number of these explanation methods, yeah, together with our proposed violation method, right? So actually we observe that there does not exist this relation, right? So the proportional relationship, right, between the violation together with the existing explanation method. So which shows that most tested explanation methods suffer from this faithfulness violation issue, right, regarding this polarity consistency. Okay, and last but not the least, we want to analyze the dominant factor, right? So which can be links to this to our faithfulness violation test, right? So we can observe that the two dominant factor, right, is the capability, right, to identify this polarity as well as the complexity of the model architecture. So we find that right. So if the numbers of layers go deep, right, so the violation increase, right? And yeah, also we show that the gradient-based method somehow to show that this can handle these violation factors. Okay, so last but not least, right? So I want to point out some challenges, right? So just now I have based on this also based on this first half session, right? So we have this we have introduced a lot of things, right, which can relate it to this domain generalization about the setting as well as the explanation methods, and also based on how do we evaluate the performance, right, which can be quite important. But so far, right, while progress has been achieved, right, there are still many limitations of these existing methods, so which calls for more attention and more research works in our community. Okay, so last but not the least, I want to do a conclusion, right? So which is okay. So there are the conventional machine learning, right, has been analyzed for many decades, and also there are many elegant theories, right, talking about this robustness and this generalization issues of machine learning model, right? So, but the assumption, right, so for this conventional method relies on that the training and testing are supposed to be similar, right? They're coming from similar distribution, but things are actually not true, right? So we call this, we always encounter this non-IID, right, cases doing that. So that's why we have the domain adaptation, right? And also domain adaptation, we also have quite elegant theory, right, to tackle this problem. So which we show that the target risk, right, is actually bounded by the training, the risk on the training data set, as well as the distribution divergence between the training and the testing data, right? So the distribution measurement actually may not rely on the label, right? So which is the setting for domain adaptation. But in practice, especially based on the real-time deployment, right? So which means that given the data, we have to do prediction, right? So we are not able to collect sufficient data to measure the distribution of the target domain. So based on this unseen target domain, right? So we have the problem of domain generalization. Yeah. So and also we have introduced quite a number of this the part related to this domain generalization, right? So as well as some related algorithms, including like transfer learning, domain adaptation, and also the multitask learning, right? We have covered. And based on these algorithms, we also have introduced like the data augmentation and data generation, and also how can we learn this environment feature representation across the domains, as well as some other kinds of learning strategy, right? Which may not designed for domain generalization, but still can be used here, right? So we also show how this method can create synergy, together with our domain generalization, and also some application, right, has been introduced. So while I mainly focus on the computer vision, but still domain generalization can be applied, right? So for many other problems, because for all data science related problem, we all encounter this generalization issue, right? Because of this insufficient data problem. And I also have introduced some data sets, right? So finally, I have introduced some like a theory, although this kind of theory has a lot of limitation, right? So which means that they are not mature, but still, they try to advance, right, this field, and want to shed light this field, right? Although there are some limitation, but still under some assumption, right? So for example, under some convex optimization, right, this kind of method still hold, right? This kind of method theory can still be applied. And also I show that this maybe at the last part, right? So how domain generalization can be applied, right? So the relationship between the explainability issue together with the domain generalization, and also I point out some future challenges. Okay, so I think that's about my part. Thank you very much.
Hi everyone, good afternoon. I'm Jin Dongwang from Microsoft Research Asia, and it's a pity that I cannot join you in person. And in fact, I have never been to Singapore before, and I can see that it's really warm in there, because you can see I'm just wearing some sweaters because it's really cold here in Beijing. Yeah, I would really wish I can join you in person. Before we start, I would like to express my gratitude to my colleague, Dr. Ha Liang from City University of Hong Kong for presenting such a wonderful, comprehensive domain generalization tutorial. And for this part, I would like to discuss some of the most recent preliminary findings of our team on the robustness of ChatGPT and other NLP foundation models from the adversarial and distribution perspective. In fact, you can just relax because it's the last part. And actually, we do not develop some new ChatGPT like models because actually we may never do that because we do not have enough resources here. It's just some kind of evaluations and perspectives. So I hope we can discuss and further to propose some new open questions. So you can just relax and just hear what I tell you in our experiments. Okay, let's get started. Okay, so let me, okay. So am I in the full screen mode? Okay, now let's get started. Okay, let me see this chat message. Okay, thank you. Maybe we all just get disrupted by the recently AIGC, which is AI generated content, because we can not only use artificial intelligence or machine learning to help us classify images, to classify the sentiment of a sentence, but we can also use it to generate something we like. Perhaps the most important thing today is the ChatGPT released by OpenAI. I'm sure most of you have already used ChatGPT to help you complete your tasks. But besides the success of ChatGPT, there are also other kind of foundation models and AIGC models I would like to mention here. For example, also released by OpenAI, it's DALL-E 2, right? It's just can generate vivid images by including simple texts. And I'm sure also most of you may have already touched it. And the next one is about music. Actually, this is developed by Google. It's called Music LM. Basically, you can just generate some music using the language models. It's very simple, but you can just try to use it. And also some kinds of advances. And another one is from OpenAI. It's called Whisper, which is a speech recognition system powered by large foundation models. And this one is actually pretty much useful. Actually, you can use it by using a simple in Google's Colab, which is very useful and very simple to use. Another one is another book in the AIGC directory is called Stable Diffusion, and it actually has created some the startup companies in the world. And last but not the least, let's not forget in the protein or in the biology area, which is AlphaFold 2, released by Google DeepMind, which is a rapid AI breakthrough in biology field. And I would like to recap you all of the disruption of AIGC. But what's the point in this research with regards to our topic today, which is domain generalization? So how can they be related? Okay. I would like to remind you that behind all these technologies, there are large language models, which is also called foundation models. You can see that this map is actually copied from this website, and you can see the size of these rounds are just the model size. You can see that GPT-3 and GPT-3.5, which is the language model behind ChatGPT, is actually not the largest. You can see that this model and this model is PALM, which is really famous, which is developed by Google. They are huge, and maybe in the not very distant future, they will just keep on going larger and larger. You can see this statistic table actually goes from 2019 to 2021. You can see that their dataset size, which is the data they use to pre-train their model, are just getting larger and larger. And we would like to know that are those large foundation models actually just close the problem of generalization and robustness? Because we can see that machine learning is mostly about the data and the algorithm. But when the algorithms are fixed, but the data set and their training algorithm and their models are kept going larger. So the problems get solved by those techniques, by those large models? This is what we are going to look after in this report. Before we start, I'd like to just recap some evaluations on ChatGPT. Actually, you will never just imagine, since the launch of ChatGPT, maybe in 2 months ago, there are also lots of papers just tries to evaluate ChatGPT on different aspects like logical reasoning, question answering, sentence tagging, and other kinds of NLP tasks. And I'm sure that today you can log into archive and search for ChatGPT. You can see almost every day there is at least one new paper about ChatGPT, which is really, really competitive in this area, right? But with the success of ChatGPT, there are also other concerns, like in education, in ethics, in medical text, and even in law. A lot of experts in different areas just expressed their concerns or their thoughts on ChatGPT. And above this, we would like to pay attention to our topic, which is domain or out-distribution generalization. So the key question here is that, is OOD generalization solved by large language models? I'm sure maybe some of you will be interested in this topic because we have a lot of training data and the large models. Perhaps we will never need to perform some OOD or domain generalization algorithms, right? So this is also what we are going to do. So let's recap the DG or OOD theorem. And in fact, this theorem is a domain adaptation theorem, which is very classic, and even it derives some new OOD or DG theorems in the new papers. So what does this theorem tells you? First, it tells you that the target risk here is controlled by the different terms, right? The first term is source risk. The second term, and perhaps the most important term in previous literature, is source target distribution divergence, which is almost maybe 99% of the papers are trying to solve, is the second term, right? The last term is also largely being ignored in recent works. It's called some complexity of the hypothesis space. So if we just put this in the large language model era, we can see that, in fact, in training large language models, there is no domain adaptation or auto-distribution generalization. They just simply want to minimize this kind of risk. So the key here is that minimizing the source risk alone, just ignoring the other terms, like maybe the most important divergence term, will just lead to a smaller or minimal target risk. This is the question that derived by this theorem. And maybe I'm wrong because there's actually no theorem on large language models, but I think we can just use this theorem to help us understand what happened and what leads to the good or bad performance in those language models. So with that in mind, I just start this very, very preliminary study, which is on the robustness of ChatGPT from the adversarial and auto-distribution perspective. Actually, this work will not be done without the help of you can see a lot of people here from my colleagues at Microsoft and from my interns and from other colleagues, the other collaborators from different universities. And if you're interested, you can just log into this web and go to see the results of this paper. But I would like to highlight some of the findings here in this paper. So let me summarize what actually we did in this evaluation paper. The task here is very simple. We just want to evaluate the OOD and adversarial robustness of ChatGPT. And so it's very simple. On what's data? The first part of the data is OOD data, because it's very difficult and almost impossible to find some really out of distribution data from the ChatGPT, because as we can see that the source data that ChatGPT has actually used a lot of the public or some not public data sets from the internet as of 2021. So it makes it very hard to find actually the OOD data set for it. So we try our best to find some new one. The new one, it means that it is released after 2021. maybe 2022, and it's very new. So our hope is that since the datasets are new, maybe they can be the OOD datasets for ChatGPT for a fair evaluation. So that's why we use these two datasets. Maybe, I'm sure most of you will not be familiar with them because they are not very popular. The first one, Flipkart, is a product review dataset released on Kaggle. It's actually released in December 2022. So it's very new, right? After a year of ChatGPT. And the second one is called DDX Plus, which is a medical diagnosis dataset. We released in last year's Europe's dataset and benchmark track, which is rather new. And we hope maybe those two datasets are new and ChatGPT will never see them. And they are OD. So that's the first part, maybe the most important part. The second part is adversarial robustness. And the reason why we adopt adversarial robustness will be explained later. But here you can see that we use a dataset called ADV glue, which is adversarial glue. I'm sure if you are doing NLP research, you must be familiar with the glue dataset, which is GLUE here. It's a very standard and a very normal dataset for natural language processing. And ADV glue means adversarial examples on the glue datasets, right? So how do we do it? It's very simple. We just query the web from ChatGPT and gather the answer. That's all. Yeah, that's maybe most works are done because we can see that ChatGPT now has it does not have an API to use. So it's very, very hard actually. And besides the ChatGPT use, we can just consider some comparisons with other foundation models because no comparison, we can never tell how good or how bad ChatGPT will do, right? So the most important part here is to design the prompts for the ChatGPT for our task. So it's the most tricky part. And thanks to our colleagues, and we will do this work well by designing different prompts to gather the results. So yeah, it's basically what we do in this evaluation. So in this slide, I would like to introduce the relationship between adversarial examples and auto distribution examples. You can see most of you may be familiar with this figure, right? So you want to recognize an image of the panda, right? So you can generate some adversarial noise by an algorithm to learn some red noise. If you plus this red noise to the panda, and then the machine learning model will just crash. It will just falsely correct it as the gibbon, which is not panda, right? So it's the very famous adversarial example, adversarial attack. So the optimization here is that to minimize the max error risk on these examples by using some perturbations like a delta here. Right. So what's their difference? We can just view them from another angle that, like in OOD generalization, although we can see that different kinds of images are different, but we can see it as some other kind of perturbation, right? So you can see that there's some painting here, maybe some photos and painting here, and there's some sketches here, and the perturbation here you can see some style perturbation, right? So by using this viewpoint, you can see that adversarial example is actually really connected to auto distribution generalization. That's why we use both of these robustness to help us to analyze in our experiments, because both are input perturbations, right? So that's the motivation of using adversarial examples. And a little about the dataset, because in adversarial datasets is not very familiar with both of you, and it is the ADV glue dataset, which is consists of some different parts of the glue datasets like SST and MLI, etc. The adversarial perturbations here are generated by different levels of perturbations, like word level, maybe add some typo and some context and some kind of different external knowledge to your input to generate some adversarial examples. The second level is sentence level, which is to try to manipulate the syntax or try to get a distraction. Distraction means to use other uncommon things to add to the text. And for human crafted examples, we do not do that, so I will not introduce them here. So this is the dataset information for this evaluation. And yeah, this is the statistics of the test sets used in this paper. Most of them are from the ADV glue. And for another kind of tasks, because you can see that ADV glue is all about classification. And beyond classification, we would also want to test the generation tasks. So we just to compose or we manipulate the ADV glue to generate a new test set called ADV glue T. T means translation. It's a machine translation task which translates from English to Chinese, because none of us knows other languages other than English. So we just test the performance from the ADV text to the Chinese text. So it's basically the adversarial robustness. For Flipkart and DDX Plus, these two datasets actually, they are not popular, but they are very easy to understand. The first one is sentiment classification, and the second one is medical diagnosis classification, which basically asks some symptoms, and then the question is what kind of symptom or what kind of diseases does this person have. So it's a multi-classification problem actually has 50 classes, so it's very hard. You can see that we only test 100 examples for this data set, but its class is 50. It's very, very many classes than the samples would just cover. So this is zero-shot evaluation because you can see we only have the browser version of the ChatGPT. But I'm sure that the results are very interesting. Here are some details I would like to tell you how do we actually do this. So it's very simple because you can see for adversarial and OOD sentiment analysis, all we do is to design some prompts to make the prompt and then concatenate with the input. Maybe the prompt here for this is the sentiment of the following sentence positive or negative. So it's the prompt used for sentiment analysis. So it must be concatenated with the primitive force of this film seems to be bubble up from the vast collective memory of the components. So it's the sentence, it keeps changing from different data sets. So ChatGPT just gives you the answer, negative or positive or neutral. So then we can manually process the results. And that's what we do. Similarly for the OD medical data set, so this is the prompt. So it's very long because we ask it to classify the symptom into 50 classes, so which is very long. But yeah, ChatGPT and other kinds of natural language processing foundation models can handle them well. Yeah. So here are some details on the QQP, and I would like to introduce it. Very similar, and it's for the MLI. Yeah, so here is the results. The results here actually is very interesting. It's parameter versus performance. So you can see the x-axis is model parameters, which is in billions, and the y-axis for the adversarial robustness, it's attack success rate. And for OOD robustness, it's the zero-shot at one score, which the higher the better. But for this ESR, the lower the better. You can see from this figure that the warm part, which this may be the warmest part, ChatGPT, it goes here and goes here in these two figures. You can see that maybe clue one is that for adversarial robustness, ChatGPT is very robust, right? Because it achieves almost the best performance than other data sets. And for OOD, it's not that bad. Yeah, it's actually the first impression. And if you compare with other kind of foundation models, actually the first two are not foundation models because they are really small. But we just want to perform some comparison on these models. And other kinds of models are foundation models. And we also compare text DaVinci and text DaVinci 003 with ChatGPT because they can be considered as ChatGPT families. Yeah. So here are some concrete numbers of the results, which is very, very, maybe, not very good news for OOD researchers, but very good news for ChatGPT researchers, because you can see that ChatGPT achieves the best performance across all the benchmarks, and it outperforms all methods, and not in machine translation. But in this classification task, it achieves the best performance, and it's the first result. And the second result is we can see that their numbers are still not too perfect. You can see that the ASR, which is the attack success rate, for this one is over 50. So it means that it's not very perfect, and there are still much room for improvement in the future version. It's the second conclusion. But the third conclusion is related to overfitting. And you can see that for this OOD robustness task, which is the F1 score, the higher the better. You can see that ChatGPT just achieved the same results as the Verda, which is a very, very small model compared to ChatGPT. And maybe we think there could be some overfitting happens on ChatGPT because there are a lot of training data and the model structure is very complex. For other models, the things are also the same because you can see that every model here is larger than the Verda. Yeah, right. So maybe for other large models, there could be some overfitting, which is maybe some good sign because you can see that due to overfitting, other large models does not perform well than the Verda. So this is actually some inspiration for OOD researchers because we can still prove that due to the overfitting, they can still outperform some large models. So this is our main findings here, and I think they are quite interesting. And there are also other interesting findings related to ChatGPT on other kinds of tasks. And if you're interested, you can just go to see the paper. And here I would like to present some case study on the adversarial examples. You can see that we adopted two levels of the distractions. The first one is the word level, and most of them are actually typo. You can see it's very simple for human to justify, right? And the first one, I think UR, because UR is not wrong because then it's a blank here, and yeah, this word original is wrong, and can and this and the language are also not correct. So I think the impression or our proposal for ChatGPT for improvement on this task is maybe they can first adopt some spell correction technique to just help them to correct their inputs. So it's very straight, right? So this one is for the word level, and for the sentence level. The sentence level here is really interesting. You can see that the error actually are also very easy for human to distinguish because maybe it's some Twitter accounts and it's some link. So another hint for improving ChatGPT or other large language model here is maybe perhaps we can use some data cleaning or some specific kind of pattern to recognize first if they are polluted like this. And then we can learn to remove those links. And this all should be done before the model training for large models. So these are two examples we just want to provide here for analyzing improvements on ChatGPT. And there's another case study on OOD examples. And yeah, it's here. This column is truth, and it's DaVinci 003, and it's ChatGPT. You can see that there's some markers on red or some kind of color to show you which part could it done wrong. Because there are normal sentences, and we cannot tell why can't they do it. So the point here is it's hard to find all the examples for large models, right? Because we do not have the dictionary or we do not have the tokens for ChatGPT. So we may never find it. Why it does bad on those kind of sentences? Yeah, so it's very interesting. Also pose another question for our OOD researchers. Would you like to just embed some meaningful words to do some research on all the examples, maybe using some explainability research to help us analyze why ChatGPT cannot do good on those data sets. I think it's very interesting. But to be honest, I do not have a conclusion here, or I do not have any proposal here to fix this or these wrong things. But I think it's very interesting to observe. And by the way, these are just some of the examples, and we provide all the bad cases which ChatGPT does not do well on our open source link. You can just click on them. So here are for the case study. So now we would like to back to vision models, because you can see through this tutorial, most of the algorithms or theorems are discussed in computer vision community, or perhaps we should just ask the question, since ChatGPT is really strong on the text data, right? So are there any vision models just outperforms all other kind of metrics in here? So this VIT-22B here is a very recent paper, and it was proposed by Google. So maybe by far it's the largest vision foundation models, because it contains 22 billion parameters, which is very huge. So this is its zero-shot transfer results on ImageNet and its variants. You can see that this is ImageNet, and these are all ImageNet-related variants of this dataset. They are very huge, and you can see that the results of this 22B version of VIT is very, very strong, and it even outperforms the fine-tuned version of the small models. So this is actually another bad news for OOD researchers, because maybe your leadership will just question you. So is your research still valuable, because VIT-22B is still very, very powerful on these tasks? And I would like to tell you that you do not, because you have an answer. Like in here, you can see that this is the results of the CLIP model, the OpenAI's CLIP model. You can see that actually it outperforms every method. I only show the results of the CLIP, but if you, you do DG research, you can see that the results are very competitive. It even outperforms almost every approach on domain-based dataset. But another shortcoming, or maybe another drawback of CLIP, is that it does not do well on this dataset. You can see that the average performance is very low, and so the reason is very interesting. Why? Because this dataset is called Terra Inc. It's some pictures taken from the wildlife animals. Yeah, so from here we can see that the trade-off, or the balance between the algorithm and the training data. You can see that a lot of the images, maybe most of the images in training CLIP or training VIT are just taken from natural images, which is not wildlife animal images, so they do not perform well. That's very easy to understand. So here I would like to tell those OOD researchers that you do not need to panic, because models like CLIP, they still have a problem recognizing wildlife animals. So maybe here we can just embed some algorithms or develop new algorithm based on CLIP to further improve its performance. So that's my answer to those questions. So is the OOD research still valuable? My answer is yes. We can still improve its shortcomings, but maybe in most common tasks we may not improve them, because they're actually doing quite good than those existing methods. So last but not least, I would like to discuss some possible directions for future research, maybe to improve the adversarial or OOD robustness in training large language models. The first one is actually what I've mentioned before. It's data cleaning. So the most important thing here is to recognize what is noise and what is not. Maybe adding some noise to the data set can actually help you to ease overfitting. But if you just remove all the noise, maybe your model will tend to overfit. It's a balance. The second part is spell correction. It's very easy, and I also introduced it before. The third part is adversarial defense. You can just train a robust prediction model or a robust fine-tuning technology, because for end users, we all just need to fine-tune some models. Maybe we can just develop some robust fine-tuning technology. And there are some very preliminary work from my team called selective forgetting fallacious weights. So we will just discuss it in next slide. And the last one is large models plus OOD algorithms. We can see that there's still room for improvement for the large models, especially on some long-tailed images or long-tailed samples. So it's very important to develop some OOD algorithms on those models. So I would like to give you a hint. It's the efficiency, because we can see large models are really hard to train. So our algorithms should be lightweight and they should be efficient. So you can refer to this paper to see how we can just develop some clip model in the federated learning setting to make it very fast. And the generalization performance is also very good. Yes, this page is just to give you a overview on this fine-tuning work. Actually, fine-tuning is very simple. We can just remove the bad knowledge, which is malicious knowledge, while fine-tuning. We can just inherit the good knowledge while just removing those bad knowledge, just implement by this neural coverage. I'm sure Dr. Hao Liang has introduced you the basics of the coverage frequency profiling or neuron coverage. And yeah, this work is just similar to that one. And we also have the same foundations like neuron coverage. You can just refer to the details of this paper. Yeah, I'm done with introducing detailed works here, and let's do some conclusion. The first conclusion is that adversarial and OOD robustness still remain a major challenge, even if ChatGPT and other models they may perform good, but the performance are still far from perfection. So the best performance brought by ChatGPT, actually, we need to develop more algorithms or just to enhance its performance on those robustness benchmarks. And finally, I would like to state again that OOD is currently not solved by large language models or large foundation models. And one hint is that maybe domain-specific fine-tuning is still needed. You can see from previous slide that the DiBerta actually achieves the same performance to ChatGPT, which tells us that we can do better domain-specific fine-tuning to improve its robustness. Yeah, that's all for today, and I would like to thank everyone for your listening here. And if you have any questions, you can post it here or just contact me after this talk. Thank you.